Okay. First, I will give an introduction and a presentation and build you, and then we will start. Okay. 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 My microphone was off. First, I will give an introduction, and then we can start. Okay. Yeah, in Spanish, because most of the public is Spanish. Yeah. Okay. Buenas tardes con todos. Es un gusto nuevamente darles la bienvenida al ciclo de conferencias SEG-UCE 2025 de Geología Económica de los Andes. Este evento reúne varios capítulos estudiantiles que hemos trabajado en conjunto para crear un espacio de intercambio académico y de colaboración entre estudiantes y profesionales interesados en la geología económica. A lo largo de estas jornadas tendremos la oportunidad de conocer investigaciones y experiencias que muestran la diversidad geológica de los Andes, así como los desafíos que enfrentamos al estudiar y aprovechar estos recursos de manera responsable. Desde Ecuador, tanto mi persona como David, presidente de la SEG de la Escuela Politécnica, queremos agradecer la participación de todos los capítulos involucrados, de los conferencistas invitados y de quienes nos acompañan hoy. Esperamos que estas charlas sean un punto de encuentro para fortalecer nuestros lazos y seguir impulsando la formación geológica en nuestra región andina. Hoy tenemos la oportunidad de aprender del Dr. Jeffrey Hedenquist, quien es asesor independiente de la industria minera en exploración y evaluación de yacimientos minerales hidrotermales en ambientes epitermales y pórfido. Jeffrey ha trabajado en 45 países para más de 145 empresas e instituciones. Ha participado en más de 440 proyectos, incluidos programas de capacitación. Trabajó durante 10 años en los institutos gubernamentales de Nueva Zelanda y Japón, donde estudió sistemas geotermales y magmáticos hidrotermales activos, así como la formación de depósitos epitermales de oro y pórfidos de cobre. Fue presidente de la SEG y actualmente se desempeña como profesor adjunto de la Universidad de Ottawa. We sincerely thank you, Jeff, for joining us today and sharing your knowledge with us. A los participantes, por favor, colocar sus preguntas en el chat y las revisaremos en diferentes pausas a lo largo de la presentación. Thank you, Jeffrey. I think we can start.
Okay. Thank you for the introduction, Stalwin. Great to be here, and welcome to everyone for the second day of online lectures on the topic of Geología Económica de los Andes. I congratulate all the students of the SGA and SEG chapters for organizing these talks. From Colombia in the north to Argentina in the south, 6 countries joining in. Today, Stalwin and David and members of the Quito student chapters organized 4 talks, mine being the first. So I will break in a few places for questions. So if people have, they can add them to the chats. And of course, at the end, we will also open it for questions. So as Stalwin said, I'm going to present a topic very important for the Cordillera of the Andes, magmatic hydrothermal systems, particularly those related to epithermal and porphyry deposits, mainly focusing on epithermal. Why? Because these systems are extremely important. They're responsible for 70% of world copper production, half of world moly, about 20% gold, and various amounts of other minor but critical elements. I'm going to start with an introduction and historical context, and then talk about processes that have formed these magmatic hydrothermal systems, particularly with evidence from active systems, followed by a variety of examples of ore deposits and a few discoveries that have been made despite dogma. And finally, look at a couple of examples of the transition from epithermal down to the porphyry environment. This is Yanacocha in Peru, the world's largest epithermal district for lithocap-hosted high sulfidation. It's produced well over 12 to 1,300 tons of gold, and a variety of volcanic domes. For example, here, Sarchaquikocha, this dome, we can see the vertical flow banding at the top. It's strongly altered to residual quartz, but it is barren, sterile. And at the top or on the margins of this dome, we see a variety of finely laminated siliceous sediments. And in some places, it's clear that there's cross-bedding. So we know cross-bedding indicates subaqueous deposition, lacustrine in the lake deposition. And not only there, but elsewhere in the district, there are finely laminated siliceous sediments and fine clastic material, even in drill core. So indicating the surface of some lakes at the time of activity. Now, if we look at an active system, such as White Island volcano shown here in 1988, in quiet eruption, degassing, large amounts of water vapor along with gases, including SO2 and HCl. Here in 2008, 20 years later, we see that the degassing activity is much less, but still with this pH 0.2 acid crater lake, we know there's still fumaroles entering groundwater at the base of this crater lake. And that crater lake, the acid fluids, they overflow and discharge along a stream, and we can see this acid altered material entering the ocean with large amounts of antacidic dissolved products. Within the lake itself, when the lake level is down, we see large amounts of muds that have been deposited here. These are laminated muds of silica colloids. And if we look closely in other places, we can see fine laminations in some places with blocks probably erupted, thrown out, that have deformed the lake sediments here, and then covered later by more siliceous sediments, again indicating that we were in a lacustrine environment. Here we can observe it, and that helps us interpret it at places like Yanacocha. So here's a view from the surface at White Island. In the background, we see these high temperature hypogene vapors, fumaroles, discharging with their SO2, CO2, and HCl. As these vapors condense, the SO2 disproportionates to sulfuric acid. And these acids form a pH less than 1, which results in dissolution, lixiviation, forming a lithocap with halos of alunita and keolnita. But on the margins of these high temperature magmatic fumaroles, we also see less than 100 degree fumaroles. These are called steam heated fumaroles, and they only contain CO2 and H2S. The acid gases have been reacted before the vapors have reached the surface. In this case, the H2S oxidizes to sulfuric acid in the zona vadosa, above the groundwater table, where there's atmospheric oxygen that oxidizes the H2S. In this case, the pH is about 2 to 3, also forming alunite and kaolnite, but not dissolving the rock, although it does form silicified horizons of opal. Here's one example of one of these steam-heated mud pools with kaolnite clays. And we can see, I'll play the video here. This is not boiling. are CO2 bubbles coming to the surface. The CO2 has been, the H2S has been oxidized to sulfate, which forms the pH 2-3 condensates that alter the rock, and the CO2 bubbles through. Now, where do we find this? In the preserved ore deposit record, ancient eroded systems. Here in Chile, at La Coipa, a silver gold deposit, we can see dacite domes such as Ladera Ferrion, discovered in the late 1970s with pyrite, other sulfides oxidized, supergene oxidized to produce these red iron oxyhydroxides. And the rock, we can see the original texture of the dacite. And here the phenocrystales have been dissolved out, and they've been infilled by sulfides or also by native sulfur, the yellow. And this rock is very, very silicious, very hard, and of course, resistant to erosion. By contrast, these other deposits, including Coipa Norte, were covered by steam-heated alteration. The horizon of alteration formed above the groundwater table, and that kind of alteration, again, alunite and kehlnite, but the rock material, the alteration is very, very fine, powdery, friable. It is not strongly silicified. Two different appearances. And so this steam-heated alteration was covering some of the deposits. So the same example as we saw at White Island, where there's hypogene vapors, strong acids leaching the rock, and low temperature steam-heated vapors condensing to form the steam-heated horizon over the top. To the northeast of Coipa Norte, in the area of Puren, one of these resistant opaline horizons is present. You can see it right through here. And below that zone and the steam-heated alteration, the Puren deposit was discovered. So we're going to come back to this example again, but this is basically the same set of processes that we see present on White Island, and here related to or overlying an ore deposit. Well, if we take a look at epithermal deposits, epithermal in yellow, porphyry in blue, first of all, we can see a spatial relationship. At least there's some relationship they're forming within, as we can see, volcanic arcs. First, the circum-Pacific volcanic arcs of Miocene and younger age rocks, volcanoes, the older Cretaceous to Eocene, Tethyan belt from Southeast Asia to Western Europe and Northern Africa. And going back in time, also the Paleozoic deposits in Central Asia, Mongolia, Eastern Australia, and Eastern North America. So these deposits, particularly epithermal, but also porphyry, they become less abundant with time. It's not that they didn't form in the Paleozoic and older times, it's simply that more and more of that older rock has been eroded to remove the epithermal and many of the porphyry deposits. Let's take a look at the relationship between volcanic distribution and epithermal porphyry deposits. Here in central Indonesia, central eastern Indonesia, the Sunda Banda Arc, we see a variety of active volcanic arc-related volcanoes in with the digital elevation maps in the brown, darker colors showing the elevation of the volcanoes. And some of those volcanoes are Merapi, recently erupted, Mount Bromo in through here, and also Kawaijin, a crater lake, pH 0.2, very similar to White Island crater lake in eastern Java. Now, in the Eocene to Pliocene times, the volcanic arc was further to the south because the slab has flattened. The the northward dipping subduction was steeper. Now it's become flatter and migrated to the north. But you can see the volcanic centers now eroded to the south with some very large porphyry deposits, Tupampitu in the Java, all the way to the most recent discovery, Onto, on the eastern island of Sumbawa, with 8 to 18 million tons of copper and 500 to 1,000 tons of gold. And these deposits are very young, mid-Miocene all the way to as young as 0.4 million years. In addition, the red areas show lithocap alteration of advanced argillic alteration. I'll define what a lithocap is in the next slides. And also the relation of epithermal deposits nearby those porphyry deposits and the volcanic magmatic centers. So it looks like there's an overlap of volcanoes, porphyry deposits, lithocaps, and epithermal veins, very close to each other. Now, how do these deposits form tectonically? As I mentioned, there was a subducting plate to the north underneath Java and the Sunda Banda volcanic arcs, oceanic subduction. We formed volcanic arcs with deeper porphyry, shallower epithermal gold, silver, sometimes base metal deposits. We also get, as in the case of the Andes, continental subduction, where there's partial melting of the subducted slab, a variety of magmatic processes at the base of the crust, at shell levels in the crust, forming the shallow, relatively shallow porphyry copper deposits, and even shallower epithermal gold deposits. These deposits are related at least spatially, but also temporally. If we go into the back arc extension environment, such as occurs, say, in the Deseado Massif of Patagonia, we find epithermal veins, but no porphyry deposits. They simply don't form in those types of extensional environments. We're going to focus today only on, subsequently, the Andes, the Cordilleran arc, and the porphyry epithermal relationships, primarily the epithermal. Now, as we can see, some things don't make sense, such as this case of an orange with the skin of a Granny Smith green apple. Now, is this an overprint? Somehow the apple skin overprinted the orange? Or is it possibly a hybrid, a new genetic hybrid, having characteristics of the two end members? The same thing is true in ore deposits. Perhaps there's one type of deposit overprinted by another, so we get a mixture of characteristics, but also the end members may not always be end member types. There may be a mixture of characteristics. So we have to keep an open mind and interpret the characteristics without putting labels or boxes on these different types of ore deposits. Now, a bit of history. Dick Silto, long ago, he's still working now, but he was quite a young geologist working in Chile in his 20s. He recognized that volcanoes with fumaroles, native sulfur deposits, etc., they probably were sitting over the top of porphyry deposits and grading upwards to epithermal. And he suggested that the fumaroles were actually the waste products, the effluentes of the porphyry forming system. Why did he think that? Because he observed that some young volcanoes in the Andes were actually eroded by sector collapse. And those volcanoes were exposing advanced argillic alteration that he saw over the tops of porphyry deposits elsewhere, more deeply eroded, older deposits in the Andes. So this is the first suggestion of this, clear suggestion of this relationship between epithermal and porphyry and volcanic centers. So that's been a bit of an introduction and history. Yes, yes, sure.
Thank you, Dr. Hedenquist. You show that the crater lake at White Island had a pH of 0.2. How does this extreme acidity impact the mobility of precious metals like gold? And what are the implications for the preservation of more sensitive alteration minerals?
Well, as I mentioned, this is the introduction. I'm getting to those topics now in this second discussion of processes and products. Basically, during the very acid stage alteration, which is formed by vapor condensation, there is no metal anomaly because the vapors do not transport gold, silver, copper, lead, zinc. So I'm going to be getting to that now in the next set of slides. So perhaps the question will be more completely answered in the next 20 minutes.
Okay. There's two questions related to the KOIPA project.
Yeah.
I can tell you because we visited that.
Yep.
In the case of La Coipa, how can we differentiate kaolinite from steam heated zones from kaolinite of hypogene advanced argillic alteration?
Well, I'll again be coming back to La Coipa in the slides on examples, but the hypogene case, the kaolinite is a halo to residual quartz, very resistant with vuggy textures, grades outwards to, again, very resistant quartz alunite, crystalline alunite, kaolinite or dickite, etc., forming in that environment. Confidently with quartz in the rock, so it's quite resistant, muy dura. In contrast, the example that I showed from La Coipa in the steam heated zone, that kaolinite is very soft, friable. It's like powder. There is not any strong silicification except at the paleogroundwater table, the opal. So again, I'll be presenting more examples of that as we go on. Any other questions? Okay, thanks. Yeah, good questions, but I hope they cover those as we go. Okay, fast forward from 1973 to 2010. Again, Dick Silto wrote a paper, very simply titled Porphyry Copper Systems. And this paper is available, open access, so anyone who hasn't read it and who is interested in the porphyry and epithermal systems in the Andes, you must read this paper. So basically, at the base of the porphyry environment with high temperature potassic alteration, there's a fluid that rises from the magma, perhaps 5-kilometer depths or more. And that fluid is a single phase called a critical fluid. Here in the fluid inclusions, it has, at room temperature, it's separated to vapor and liquid, but we can also see very small tetragonal crystals of chalcopyrite with up to perhaps 0.2 weight% copper in this fluid. That is the parent fluid for forming the porphyry deposit. But as the fluid continues to rise, it cannot stay as a single phase. It's maybe 500 degrees, 600 degrees. It hits what's called the solvus. It starts to separate from, say, 5 weight% critical fluid, NaCl, to as much as 50 weight% hypersaline liquid. That's in equilibrium with biotite, magnetite, K-feldspar, potassic alteration. And we can see these hypersaline crystals with salt, sodium chloride, potassium chloride, iron chlorides, the red, etc. Now, how do we change this ascending fluid from 5 to 50 weight%? By removing water vapor, and coexisting with those inclusions are vapor-rich inclusions. We have to remove almost 90% of the water to go from 5 to 50 weight% salinity, and therefore this vapor is the dominant water product in the system. The vapor is low salinity, therefore it's buoyant, and it rises. It rises to discharge, for example, at White Island, this passive degassing. But as it does, part of the vapor condenses into groundwater to form the acid condensate, forming residual quartz, alunite, kaolinite. And that forms the lithocap, which is the lithologic horizon that hosts the advanced argillic alteration, a core of residual quartz, silica residual, possibly with vuggy texture, out to quartz alunite, halo, quartz kaolinite, quite resistant. And that vapor, and therefore that alteration, is linked to potassic alteration, the hypersaline liquid. So that is why we see this spatial relationship between epithermal and porphyry. It's because they are genetically related. It's now very clear. 40, 50 years ago, it was not so clear. There's still a lot of argument. I think there is no longer any argument. Now, this vapor stage at the epithermal environment does not have metals. It's sterile, barren. Whereas the epithermal mineralization may form in the later magmatic stages, when a low salinity liquid, 5 to 10 weight%, rises into the system and forms either the gold copper mineralization in the residual quartz or the epithermal veins with gold, silver, or silver gold, plus maybe sphalerite and galena. And at the same time, we're getting mineralization of the porphyry deposit, porphyry copper deposit at depth, or the proximal skarns, proximal to distal skarns, or the carbonate placements, or the distal disseminated gold deposits, such as Carlin in Nevada. So that's the schematic, and I'm now going to take a look at a few more active examples to stress the nature of that hypogene vapor. Here at Satsuma-Ujima, it's a 1,000-year-old volcanic dome, a rhyolite dome. We see strong alteration here, and like at White Island, high temperature vapors discharging, 800 degrees, with SO2, HCl, CO2, H2S. But we measured the gold only 1 to 2 part per trillion. That is very, very small 10 to the minus 12 amounts of gold in the vapor. Now the vapor condenses, the SO2 again combines with water to form H2SO4, the sulfuric acid and the HCl disproportionate during cooling and become more and more acid. And that vapor leaches the rock. Here, this is rhyolite with 97% silica. The 97% silica was rhyolite. The only way to get 97% silica in a rhyolite is to leach the sodium, potassium, calcium, magnesium, iron, and aluminum, etc. And so this volcanic gas chemist is thinking about the volcanic processes that led to this leaching. And we see near the summit, cristobalite, up to 97% silica, elinita, and less than 2 ppb gold in the alteration. Only one sample that was collected contains 29 ppb, parts per billion, gold, and that's related to some sublimates. So the dissolution, lixiviation of the rock forming the residual quartz, but it's sterile in this early stage with low, less than tens of ppb gold. Now, if we go onshore, here we can see South Ujima active on the horizon, here just south of Kyushu. If we go onshore, we can find 4 million-year-old hypogene quartz alunite related to the Nansatsu deposits called Iwato. Here we see the Iwato deposit with residual quartz hosting mineralization. The pyrite has been supergene oxidized, so we get a lot of iron oxyhydroxides, the reddish color. If we look at a plan map, we see residual quartz almost 900 meters elongate with narrow halos of quartz alunite, quartz keelnite dicite in orange and yellow. Here we can see Professor Urashima standing right next to the mineralized residual quartz, a halo of quartz alunite out to clays. Or here, next to the feeder zone, going down from the lithocap to dicite alteration. Now, if we take, this looks like it's a one elongate residual quartz with bodies, greater than 1 gram gold bodies in areas within the residual quartz. But in long section, we see something different. In the underlying andesites, which were not permeable, the fluids, vapors, rose along fractures. And those fractures, once the fluids reached the shallow permeable tuff, there was permeable outflow, mushrooming in hongo in Japanese, and that mushrooming led to the coalescing of the residual quartz bodies. Also, the gold deposits, gold mineralization, have the highest grades in the feeder zones, the root zones of the mushroom residual quartz, the lithocap. So this was the first identification of lithology, permeable lithology, forming a lithocap, subsequently called lithocaps by Silto in 1995. Now, this is one example from Colorado called Summitville. Here we can see, in contrast to Iwato, we see a large area, grids of 1 kilometer, a large area of quartz keelnite in yellow, with narrow zones of residual quartz, quartz alunite. And if we look at the high-grade stopes of the old-time miners, greater than 10 grams per ton gold, we see that they're elongate also. Elongate along structures. Now, this was a monzonite dome And those structures are very narrow. And quartz alunite, residual quartz here forming hills. And the alteration, the grades are highest along the structures, but very low grades in the narrow halos, 0.3 grams around the residual quartz. So it's the residual quartz alunite that is that the most of the mineralization is forming in, and that goes everywhere in the world. So here we see one of these fractures with residual quartz, and this is the ore body. And on the margins are the quartz alunite halos out to kaolinite dicite on the margins. If we look at the contact between the residual quartz and the quartz alunite, we can see that the monzonite with large phenocrystales, here the phenocrysts are altered to alunite, but to the left, they've been dissolved. So we know that at pH less than 2, aluminum becomes, aluminosilicate minerals and alunite becomes soluble. They dissolve and leaving residual quartz. So that is the paleo pH 2 contact. And this is a typical zonation pattern within this type of deposit of within the feeder zone, we have residual quartz mineralized in some cases to quartz alunite, quartz kaolinite, out to clays, illite, montmorillonite, etc., to chlorite with feldspars and fresh rock. Why do we see that zonation pattern? Because residual quartz is stable at a pH less than 2. Alunite and kaolinite at pH 2 to 4. The clays stable at pH 4 to 6. And greater than 6, the feldspars are still stable along with chlorite. It's a simple zonation of as acid fluids, condensates are reacting with the rock, they become less and less acid as they go away from the halo. And this zone can be tens of meters wide, as in Summitville, residual quartz about 5 meters, quartz alunite here, whereas it can be hundreds of meters wide, such as at Yanacocha, a much larger system. And importantly, these residual quartz bodies, they flare upwards. Why? Because as the temperature decreases, the acids dissociate and become more reactive. We also see deeper tennantite and chalcopyrite, and at shallower levels, enargite covellite. Now, I'm not going to talk too much about sulfidation state, but basically this change from intermediate to high sulfidation state of the sulfides is also due to cooling of the fluids. If we had more time, I could discuss these details, but here we see, for example, this upward flaring of the alteration and the residual quartz forming at shallower levels within this monzonite dome, along fractures, as well as on the margins, the fractured margins of the dome. And with that part of that dome altered. So in this case, the alteration was only along the fractures because there was no lithologic permeability in this monzonite or quartz latite porphyry dome. So to summarize, lithocaps are the advanced argillic alteration along a permeable lithology, but with feeder zones, root zones, extending down along fractures or perhaps along contacts of intrusions, domes, or diatremes. And all lithocaps have feeder zones. We have to have some way to get the vapor, acidic vapor and condensates up to the permeable lithology. However, not all feeder zones, as we saw at Summitville, not all feeder zones have lithocaps. If there was no permeable horizon. So here is the residual quartz from Summitville with the large phenocrystales, the small phenocrystales dissolved away, and on the margin, the same rock, but at higher pH greater than 2, the phenocrystales altered to hypogene alunite, crystalline pink alunite. And overlying that hypogene alteration is the possibility of having groundwater table controlled blankets of steam heated alteration, 2 different styles of alunite and kaolinite. Already there was a question. This alunite kaolinite will be very muy dura, very resistant to erosion, and this kaolinite alunite will be easy to erode because it's muy friable. And importantly, the early lithocap formation is sterile, barren, but it's possible that if there's a later liquid rising into the system, metals are brought into the system, forming the highest grades in the feeder zone and migrating out along the permeable lithology. Any questions, Stalwin, that came up over this? Yeah? Good question. And one of my next slides, let's see, 3 slides from now is going to answer that. So on one hand, there can be a relationship. On the other hand, there is no relationship. It's complicated, as I'll show. Other question? Well, in Patagonia, those are related to extension. Some people have suggested plume magmatism, but let's say major crustal extension. It's the second largest or the largest ignimbrite massif in the world, extending down to Antarctic. I think the largest, as I recall. And those magmas, we have bimodal basalt felsic magmatism, and it's those 5-10 kilometer deep magmas that are exsolving at least some metals to form those epithermal veins. Unfortunately, I don't have time today to go into all styles of epithermal. I'm focusing on the styles that form primarily in the Andes. And we can have perhaps another lecture some other day on the Deseado style of epithermal deposits, except there are some lithocaps, unfortunately none mineralized, but there are some lithocaps in the Deseado massif as well. So it's an interesting place, a lot of potential, and perhaps we cover that some other day. Another?
Okay, and the last one from Marco. Excellent presentation, Dr. Hedenquist, and congratulations to the SEG-7 chapters. Could you explain if the host rock composition significantly affects the style of grade of the high sulfidation mineralization?
Yeah, good question. Not that I'm aware of. Most high sulfidation deposits, lithocap-hosted deposits, form in andesitic to felsic, rhyolitic, volcanic rocks, but there are some that are related to granites, although these are Jurassic granites. I'll discuss one in a few slides at Pascua. That was simply the host rock. Another in the La Libertad district of central Chile, there is the Lagunas Norte deposit that is hosted by the Chicama and Chimu sedimentary formations of sandstones and siltstones. And the characteristics overall are very similar, except that the host rocks already are siliceous, quartzites and whatnot. So we don't see a texture of, say, of vuggy quartz, because there was nothing to become vuggy in those sandstones. So we have to interpret what was the original lithology. And all of those are forming world-class deposits. Lagunas Norte, 9 million ounces gold. Pascua Lama, 15 million ounces gold, even though they're hosted by sediments and granites. So interpret the rocks, the host rocks, by looking closely. Okay, go on. Yep. Well, as I said, residual quartz is very, very resistant to erosion. Muy dura. Here, this is residual quartz in the Mulatos district of Sonora in northern Mexico, with cliffs of 200 meters or more. And since this type of alteration is a principal host rock to high sulfidation mineralization, this type of rock has to be sampled. Of course, very safely. We have to have protection for people doing sampling, but it must be sampled. I've been places where everything around the residual quartz cliffs has been sampled of, say, quartz alunite, quartz clays, but not those cliffs. And that is where we have the best grades. So we must get and sample those steep cliffs, but safely. This is across the border in forget the state, pardon me to the Mexicans here, but Sasal, Mexico. And we can see again, the very steep cliffs developed in residual quartz. And the first geologists stopped in this valley in the quartz dicite zone, found low grades, but the mountain climbing geologists went up this cliff and found good grades. So we must sample those steep cliffs of residual quartz. So I'm going to talk now, though, everything from here on will be in the Andes, from, in this case, southern Ecuador to central Chile, where there are belts of lithocaps, not continuous within these areas of orange, discontinuous, but there are many, many lithocaps within these zones related to old volcanism. And here in particular, in central Chile, we're going to look from the El Indio belt north to El Salvador, to the southern end of the Maricunga belt. And some of the examples I'm going to talk about, starting El Indio and Pascua. Then we'll be talking about Quimsacocha in Ecuador, Audentani Cañawiri discovers in southern Peru, of course related to Yanacocha in northern Peru. And we've also already mentioned La Coipa, but then discuss Salars Norte discoveries here just south of the Maricunga district. So that's the general location of the examples I'm going to talk about in the next several slides. Now, to address one of the questions, here are the outcrops of residual quartz in red of deposits districts, here in this case, Yanacocha in northern Peru, very large deposit. Somewhat smaller deposit in northern Peru, Parina, and we can see smaller area of outcropping residual quartz, but it extends beneath this outcropping quartz alunite zone. We go to Sasal that we just looked at in Mexico. It is smaller area of residual quartz, smaller quartz alunite, again, smaller deposit, 3 million ounces. Tucari, I'm going to talk about, a bit smaller area of residual quartz, quartz alunite, 2 million ounces. Sipan, west of Yanacocha, large area of structurally controlled quartz alunite, one small residual quartz on the margin of the body, about 1 million ounces of gold. Summitville, also mineralization along narrow structures with large area of quartz kaolinite alteration, even smaller. And some deposits with very little residual quartz just along structures of hypogene quartz alunite, quartz kaolinite, etc., very small amounts of gold. So there looks to be relationship between size of residual quartz and size of gold mineralization. However, there are some deposits here, such as El Indio, which is a very large deposit, but you can see the size. It is 200 by 100 meters in size. Why? Very high grades along structures. That's why, in fact, this exploration was done in the Kamchatka Peninsula, looking for high-grade structures that might be mineralized like El Indio. I should also say that there are some large lithocaps, almost as large as Yanacocha, that have less than 10 ppb gold. So they are barren lithocaps. So we almost also have to keep that in mind. Certainly, having a large area of residual quartz alunite is good, but it doesn't promise that we're going to have large amounts of mineralization. Each prospect has to be assessed on its own merits. So here at El Indio, in central Chile, we see shallow horizon at 4,400 meters of lacustrine sediments with kaolinite, but also native sulfur in these sediments. Steam-heated alteration of lacustrine sediments. A bit like we might see in the Crater Lake at White Island. Well, here the plant was built at 3,900 meters, a little bit of surface alteration, but most of the hypogene alteration with mineralization is at depth, covered by these areas of steam-heated alteration at 4,400 meters elevation. Whereas at depth, 4,050 meters elevation, that's the level of this plan, and this shows now the zone of porphyite, kaolinite, alunite in orange, and structures controlling early enargite veins in gray, cut by later gold quartz pyrite veins in red. Now, these are hosted by the advanced argillic alteration, but in some places where the veins cut into the wall rock propylitic alteration, those veins actually have halos of white mica. So the fluid depositing the gold was not very acid. It was white mica stable, in contrast to the where those veins were cutting advanced argillic alteration, all the potassium was leached. So there was no potassium to form white mica alteration. Now the mineralization here is associated. Here it was a gold copper alloy, hence the brown color, associated with chalcedony, silica gel, and high grades of gold plus pyrite. That was the high-grade mineralization with an average grade of 200 grams per ton gold. That's why such a large deposit of large gold production was found within a very small area, 200-meter grid in through here, because it was strongly structurally controlled, in contrast to many lithocaps that are disseminated, grades of 1 gram per ton or less. This shows the enargite veins being cut by the direct shipping ore of the gold pyrite quartz or residual quartz veins. And these are the veins that were outlined by the geologists, drilled, blasted on this floor, everything scooped up, sent by boat to copper smelter in Japan for the quartz to be used as copper flux and recovering all of the gold as a byproduct to the copper smelting. So as you can see, again, 200 grams average grade. The cutoff for the direct shipping ore was 100 grams per ton. In the first few years, they produced 1.5 million ounces of gold. Total production, 8 million ounces. So early pre-ore, alnite, kelnite, etc., followed by the mineralization stage, early enargite, pyrite, the copper mineralization stage, and then overprinted by the gold mineralization stage, the direct shipping ore along structures, both cutting enargite veins, but also cutting out into the propylitic alteration. And here we can see the gold was associated with chalcopyrite, tennantite, sphalerite, intermediate sulfidation state sulfides, as well as tellurites, calaverite, altite, goldfidite. So that's an example of very high grade, high sulfidation deposit. And I should just remind everybody that this early leaching stage was sterile, barren. Mineralization came later. Well, if we go only 100 kilometers to the north, Pascua, back in the 1990s, when I visited here, 1994, called still Nevada, this area covered by large steam-heated alteration. And at the time, the exploration was being done deep because El Indio was deep below steam-heated alteration. But then Raymond Janis assessed this area, started sampling the steam-heated alteration. He discovered 2 million ounces of gold hosted within the steam-heated alteration that had overprinted the gold mineralization, overprinting due to a lowering of the groundwater table. Well, subsequently, the adjacent area was explored, large area of steam-heated alteration discovered at Lama, Pascua and Lama. Here, this is Argentina, across into Chile. Here we have supergene jarosite, and iron oxyhydroxides. A cross-section through here shows this very thick kelnite in green, steam-heated kelnite alteration, overprinting the granite-hosted residual quartz, and the residual quartz hosting the high-grade mineralization, up to 4 grams gold. You can see the roots high-grade and the lithocap in the granite. So those vapors rose along fractures, structures, permeable structures, then leached the rock and formed their own lithocap in the much older granite, not volcanic hosted. So that's why we have to consider all host rocks, intrusions, sediments, as well as volcanic rocks as potentially hosting these systems. Here we move on to, or back to, La Coipa, where mineralization of Ladera-Ferron, this dacite dome, we can see the residual quartz, the steam-heated zone overlying Cancan, Brecha Norte, and Coipa Norte. This is a flat-lying, steam-heated kelnite alunite zone. Why flat-lying? Because groundwater table is flat-lying, and the H2S oxidation only occurs above the groundwater table with atmospheric oxygen. So that's why we get this lower temperature, friable kelnite alunite. And as I pointed out, Puren, here to the northeast, discovered below steam-heated alteration. If we take a look at Puren, this southern area, here was the the opaline horizon, but overlying the opaline horizon is steam-heated alteration. Drilling did not discover any mineralization here, but through some geochemical anomalies, they were able to find Puren Norte below a steam-heated cap, steam-heated blanket, a couple kilometers to the north, and underlying that is quartz and illite zone. In fact, this is not a high sulfidation deposit, it's an intermediate sulfidation deposit, neutral pH alteration, with silver-gold mineralization hosted by the quartz. At surface, in the steam-heated alteration, only very low concentrations, 3 ppm silver or less. But fortunately, very careful work being studied or being conducted in this area, geochemistry, geophysics, good geology, and knowing that steam-heated alteration could be barren, they finally discovered this deposit blind. And once it was mined, here we can see the flat-lying steam-heated kelnite horizon. Again, flat-lying because that was the paleo groundwater table in the blue line, dashed blue line. And it's at that paleo groundwater table that we have the low temperature silicification, opaline silicification of the groundwater table. The opal can be quite resistant. So even if the very easily eroded kelnite is removed, you may preserve the opaline horizon at depth or at the surface because it's much more resistant to erosion. Now, the Placer Dome geologists discovered this deposit, but then Goldfield geologists exploring to the north, they came here for a visit to learn about the characteristics of this deposit. And subsequently, the Goldfield geologists then went from La Coipa to the northeast, where they're exploring here in young Miocene rocks. This area was 10 to 15 million years. They're looking in areas of 5 million year rocks, but also with large areas of steam-heated alteration. They assessed 3 areas. They did not find good results. Some gold mineralization at Pircus. Finally, the most difficult to get to, the highest elevation, was Salares Norte. Now, the reason that they were here, because they'd visited Puren. So they used the Puren model to explore in this area of steam-heated alteration. There was a lot of ground available because the elevation was high, 4,000 to 5,000 meters, difficult to work, a short field season. And they used spectral anomalies from Aster to identify altered corridor. They selected 4 targets for follow-up work on the ground. These 4, the last one was Salares Norte. And Salares Norte was the discovery. Now, first of all, they had Aster and Landsat evidence that there was this topographic high here being altered to alunite and kelnite. And using the Landsat signature, the light blue being opal. So that already told them, well, this may be a steam-heated alteration. The eventual discovery was at the location of this red diamond. Now, if we go to the surface and look in this direction to the south-southeast, we see overlooking the area that is in fact a dome, a dacite dome that was steam heated on the margin. We look further to the east. We see this caldera formed further east and very young volcanic resurgent domes, volcanic stratovolcanoes. And This was in 2008, just after the discovery. 2011 was the discovery. They started working in this area in 2008. Discovered in 2011, found a resource by drilling at 2015, and by 2021, they were now mining down to the top of the ore body. A great discovery, 27 million tons of 4 grams gold, over nearly 4 million ounces of gold. Now, here's the dacite dome again, steam heated alteration. And on the margin of the dacite dome is a place they called breccia principal. That breccia principal is a polymictic breccia with wispy juvenile clast. The wispy clast tells us that this is a diatreme. Now, some of the characteristics of this area are the breccia principal diatreme breccia, as well as hydrothermal breccia, advanced argillic alteration, residual quartz, allanite, etc. Now, they did soil sampling, but the soils here are actually talus fines, and they also sampled outcrops, rock chips, but the anomalies, although there's some epithermal anomalies, arsenic anemoid, etc., the rock chips only 35 part per billion. Many managers will not drill such a low anomaly. And the talus fines, equivalent to soils, they had less than 24 ppb, except for one sample, 0.6 grams per ton gold. However, they knew from their visit to Peren that steam alteration does not have significant anomalies, so they weren't worried. They also did some geophysics, magnetics, CSMT, identified a high resistivity zone, and they'd already had confidence at Pircus, one of the other prospects, and so they drilled 2 holes. The first hole it failed at 85 meters depth. The second hole, RC hole, basically at 96 meters, well, at about 180 meters, they cut almost 100 meters of 1.5 grams gold. That was the discovery. So cross-section to the discovery, we have a variety of advanced argillic alteration, but the advanced argillic alteration within the diatreme breccia was hypogene quartz allanite, kaolinite dickite, and associated in this breccia, associated with silica gel and high grades of gold, visible gold, VG, within the siliceous, the silica gel, creamy silica gel, cementing these breccia clasts, in this case, up to 1.5 kilograms per ton gold. And then there was the steam heated alteration, flat-lying alteration, and flat-lying opaline horizons in this light blue. And that defined, of course, the groundwater table. The base of the opaline silicification defined the groundwater table. And subsequently, any pyrite in the rock was later supergene oxidized. After mineralization, oxidized and producing iron oxyhydroxides, jarosite, etc. So 3 types of advanced argillic alteration, but 3 different types, 3 different environments of formation. We have to be very careful to describe those various types, their characteristics, because in this case, hypogene is related to mineralization. Steam heated blanket could be far away from the hypogene source of the system. And also supergene oxidation products could be away from the mineralized center of the system. So measure the mineral, determine the mineralogy, describe the textures and other characteristics, the morphology, and maintain that information rather than just lumping them all together as advanced argillic alteration. As I said, 3 environments of formation. Here, the hypogene, SO8CL, forming hypogene fluids, pH less than 1, H2S oxidation in the above the groundwater table, forming steaming alteration, and then late pyrite oxidation above the groundwater table also, forming supergene alien kilnite. If we take a look at mineralization, we see that the top of mineralization is very sharp. That was the top of the groundwater table. 4370 meters elevation here at Brecha Principal. We can see the groundwater table defined by opaline silicification, 4370 meters. So this was the top of the hydrothermal groundwater table and the area of high gold grade mineralization. With the high grades associated with silica colloidal, creamy silica gels cementing the brecciated fragments. In this shallow part of the hole, 80 ppb gold here, 100 meters deeper in the same drill hole, 1 kilogram per ton gold mineralization. So gold rising up to the groundwater table, silica in some cases rising higher, but a sharp top to gold mineralization. So I have some more examples to discuss, deposits that were first explored, but then people walked away, and subsequent discoveries. So it's discovery despite dogma. Stalin, are there any questions?
Yeah, yeah. There's quite a few questions.
Okay.
One from Paul. What is the relationship of the epitermal lithocap with respect to copper porphyry when I have strong anomalous values of molybdenum in the lithocap's area?
Well, second comment first. Lithocaps can be mineralized, can be anomalous in moly, yes. But not as much, I think, as the porphyry deposits. But remember back to Silito's porphyry copper system, and that's the whole system, not just the porphyry copper deposit. The lithocap sits over the top of the porphyry. But of course, the lithocap can be elongate. So we shouldn't just drill through a lithocap. We may be missing the intrusive center in the porphyry. We have to look for the feeder zone of the lithocap. And I'm going to be talking about how to find the feeder zone in the next example. Next.
Okay, this is from Diego Chamba. He says, I studied a high sulfidation target developed over a metamorphosed Jurassic granite, where mineralization occurs under structural control within these rocks during the Miocene. This process causes the metagranites to transform into mylonites, completely replaced by residual and baggy silicate. Do you know any other deposit of this kind?
Well, not strongly metamorphosed rocks, but of course the Chimu and Chicama sediments in La Libertad district of Peru have been folded, and there's been some diagenetic alteration there, possibly some metamorphism. Higher grades, I've not worked in higher grade metamorphic rocks, I'm sorry to say. Is this deposit in Colombia or Peru? Ecuador. Oh, okay. Well, I'm sorry. I don't have experience, but I mean, as I said before, granite hosts, sedimentary hosts, volcanic hosts, also metamorphic hosts. If the intrusive system is there, the vapor condensate is going to be acid enough to leach any rock, including metamorphics. So good luck. Next.
Okay. In low to intermediate sulfidation epithermal systems, how do temporal and spatial variations in alteration mineralization zone, particularly the transition from alite to smectite, alite-smectite to advanced argillic assemblages, reflect the evolving chemistry and redox state of ore-forming fluids? Can these alteration patterns be quantitatively linked to changes in magmatic gas input during the waning stages of the
Well, that's a
hydrothermal?
complicated question. It would take me an hour to answer it, and also discuss some other aspects we're not talking about tonight. Alteration really is not affected by the redox stage of the fluid. Of course, the magmatic nature of the magmatic fluid is controlling the style of alteration. But where we have acidic fluids, when they react with the wall rock, they neutralize, as I'm going to show in another slide. Also, I showed at Summitville that systematic zonation. But in terms of waning stages, I mean, certainly the early porphyry formation, potassic alteration, the early very high temperature magmatic hydrothermal fluid, that's when we create the vapors and the vapor condensates, get the acid alteration. And it's the later magmas. You could read Shinohara and Hedenquist 1997 Journal of Petrology to talk about the evolving magmas. The late magmatic fluids, those stayed liquid. They're lower temperatures. They stayed liquid as they enter the epithermal deposit. I really don't try to track the redox stage, etc., of the magmas from the epithermal fluids, even though they are related. But as I say, a complicated question, and really takes a lot of time to adequately answer it or address it. Next.
Okay, another from Diego. In a deeply eroded system, what is the significance of finding diaspore versus pyrophyllite? Do they represent distinct temperature regimes or different fluid pH conditions?
Not really. They overlap in pH and also in temperature. I'm going to show that in a slide, a couple of slides from now. Of course, diaspore is not aluminum oxide, and it forms. It can form at silica undersaturated conditions. But basically, if you find one or the other, they're indicative typically of higher temperatures, 250 to 300 degrees or more, and relatively acidic conditions. Again, to go into the details, I'd have to pull up another diagram. I don't have a phase diagram, but by reading Julian Hemley's study in economic geology in 1980, he addresses the stability of pyrophyllite versus diaspore. But basically, they're indicating very similar conditions. Anything else?
Another from Daniel Hughes, his fellow from Argentina. What indicates the
Well, it
presence
indicates
of
you're at the base
epithermal
of the
muscovite in the
lithocap,
base of a lithocap?
and I will talk about it briefly in my last example. For the sake of time, I cut out some more examples of really the transition down into the porphyry. I only have one example. But, for example, at Valeriano, many porphyries in Chile, etc., the white mica muscovite overprint of the top of the porphyry, as the fluid is rising. I'm going to have one phase diagram to demonstrate it here. As fluid is rising, it cools from muscovite stability to peroxide stability. And I don't see muscovite forming within the lithocap. It's at the base of the lithocap. And it's this transition to peroxide that is basically defining the base of the lithocap. If we are coming from top down and we get to peroxide and muscovite, then obviously we're below the lithocap. We should keep drilling. Anything else?
Okay, two more. One from Camilo. Watching the slide of size of alteration zones, can we conclude the permeability of rock or the volume of fluids are directly related with the volume of resources?
No, because as I said, I didn't put in the example, but there is one example of a lithocap in Mongolia that is the same size as Yanacocha lithocap. It contains less than 10 part per billion gold. It is a barren lithocap. The liquid did not reach that horizon. And so the size of the lithocap doesn't necessarily say anything about the potential resource. If I had a choice between a small lithocap and a large lithocap, I might choose the large lithocap to assess, unless there was some evidence for high grades associated with a small lithocap. But again, didn't have enough time to go into all the details and examples, but you can have large barren lithocaps. So you have to be careful of those. In those cases, drill the feeder zone, find the feeder zones. I'm going to show you an example of how to find the feeder zone in a moment.
Yeah, okay, this is related to one from Miguel. How does the formation of a lithocap controlled by lithology differ from one controlled by structural feeders?
Well, lithology usually is flat-lying. Structures, whether a big fault or the contact of a dome or a contact of a diatreme, they're high angle. And those structures provide feeder zones from depth, 2 kilometers depth, to guide the vapors to the surface. They condense. And if there is a permeable lithology, then they, like we saw at Nansatsu, Iwato, then they can flow into the permeable lithology to form a larger residual quartz zone, lithocap. But in the case of Summitville, the dome-hosted mineralization the dome-hosted alteration, the dome had no lithologic permeability. So it was only fractures cutting through the dome. That's why all of the alteration is along the residual quartz is along fractures, and the high grades are only along those fracture zones. No significant tonnage developed out into the lithology because it was not permeable. Okay, good. How about if we have a 3 or 4 minute break? If people want to get another cup of tea or maybe coffee, or maybe people are already drinking beer, I don't know, but 3 or 4 minutes, okay? Sounds like someone has a dog with them. It's Darwin's, okay, as I expected. 3 or 4 minutes. I would have thought that they would have left it there, but. How's it going, Stalin? Okay, good. Well, back to Yanacocha. Here we saw that sterile dome, residual quartz, but underneath is a deep deposit on the flanks of the this dome called Chaquicocha. This here is Carachugo, and Carachugo is a lithocap. There's a San Jose ignimbrites that were permeable to residual quartz, to vapor condensates, forming the residual quartz with subsequent gold and enargite, now oxidized in the lithocap. You can see the margin of slightly, if you can imagine, it almost looks a little bit browner, lighter color, darker brown. And then here, the clays and pyrite. It's actually slightly gray. Well, Newmont geologists decided to explore in the region. They went north with this idea in mind to southern Ecuador and to this massif about 4,000 meters in the area of Cuenca. And they had the Yanacocha model that the lithocaps outcrop at the surface with gold mineralization. And so they joint ventured in 1993. They drilled almost 8,000 meters in 82 holes, but average depth 93 meters. Why? Because everything was less than 100 meters deep at Yanacocha. And they didn't find much in their drilling, but one high grade, 2 meters of 83 grams gold. In 1999, joint venture with IM Gold and the landholder, the structural geologists recognized this high grade interval and thought, oh, perhaps there are structures controlling the high grade. They finally started drilling in 2002, but their average drilling was 330 meters. And 18 months later, they discovered in hole number 40, 100 meters of almost 10 grams gold, eventually defining about 3 million ounces of gold. So Newmont had this unfortunate dogma that they should only drill a shallow depth rather than assessing the characteristics of the rock. Here we have a cauldron with a series of andesite flows away from that circular structure. There was in the blue, a diatreme with porphyry copper fragments, up to 0.2% copper in the porphyry copper fragments, and through here, subsequently intruded by dacite dome. So I knew that there was a porphyry system at depth, an intrusive center at depth. So definitely a good target B. And with northeast, southwest structures, regional structures cutting through the volcanic rocks, also north-south structures. The next slide will show Newmont's mapping, same area, the diatreme, the circular structure, a large amount of quartz alunite to the north, the purple colors, and to the southeast, areas of vuggy and residual massive quartz with some anomalies. Well, Newmont focused largely here, but also a little bit to the north, but the subsequent discovery was made in an area of almost no surface outcrop, Quimsacocha, now called Loma Larga. The important slide here is that when you look at the stratigraphy, you see the lapilli tufts in yellow with sandwiched between not just one but several andesite lava flows. Andesite lava flows being low permeability, the tufts having high permeability. And the upper horizon of tufts were permeable and were altered to siliceous horizons, and that was the horizon that Newmont had been drill testing, the upper 100 meters or so. Whereas IAMGOLD's drill holes were testing a lower horizon, residual quartz developed in a lower tufaceous horizon, lapilli tuff horizon. Here we can see this lower residual quartz, vuggy texture, vugs after pumices. So this was an unwelded tufaceous horizon with open spaces after pumices, as well as fine open spaces after fine phenocrystales. So multiple lithocaps and with only the lower lithocap mineralized. So now the question is, where's the feeder? In this section, we see no feeder, but always there is a feeder zone. Well, if we take a look at their drilling, we see some of the early holes. We see one hole here cutting the deeper residual quartz zone lithocap with 1.4 grams gold. Another hole here, 1.3 grams gold. Both of them have narrow zones of kehlnite, illite, outwards to smectite, the green. But then this drill hole here, again, low grades of gold, 1.3 grams gold, but the upper halo had a mixture of porphyte, dicite, alunite. Well, they went in this direction. This hole had hanging and footwall zones of porphyte, dicite, alunite in orange. Now, to address an earlier question, kehlnite has indicates temperatures of formation of 100 to 200 degrees. Halloysite lower, dicite higher, 200 to 250 degrees. And porphyte and diaspore, higher temperatures yet, 250 degrees and above, along with zunite and topaz, under acidic conditions. And so it's very clear that the indication of the paleo temperature is increasing to the south. Well, where should we drill? North or south? Stallman, who's raising their hand for north? Anybody? Who's raising their hand for south? Well, those suggesting to the south would be correct. Here was hole 122. It intersected a feeder zone. And that was a temperature, that was direction to the higher temperature feeder zone, which was recorded in the alteration proximal to the feeder zone, as opposed to distal, where you get only kehlnite and smectite clays, which form at temperatures less than 200 degrees, 150 degrees. Well, here's another section showing that hole 122 through the feeder zone, 100 meters of almost 10 grams gold. The lower grades, 2 grams, 3 grams, 2 grams in the lithocap. But at 150 meters depth, the lower grades were not going to be economic. They needed the higher grades in the feeder zone. Of course, you can get local areas of some grades higher at the shallower levels, but not consistently. And so that was the discovery of Kimsikocha, now called Loma Larga, by using structure, lithology and stratigraphy, alteration mineralogy, etc., putting it all together and targeting, finally getting a target into 122 drill hole. And here we see the enargite, pyrite in this brecciated zone. 17 grams gold, 68 grams silver in brecciated residual quartz. So 2 lithocaps, multiple lithocaps, with the shallower level sterile, barren, because the early vapor that rose to form that lithocap, that permeable horizon, did not have metals in it. Subsequently, liquid ascended to the lower lithocap, and that liquid decided to follow the permeable lithology at depth and not rise very much to shallower levels. Well, when I first visited this area, a kilometer to the southeast, we walked into a valley. We found a narrow quartz vein, 30 centimeters with enargite gold, but didn't quite appreciate the importance. Whereas that 3,600 meter elevation horizon is exactly the horizon of mineralization, is basically the manto. And if we look at a long section, we see all of the mineralization is at that 3,600 meter plus or minus 20, 30 meters elevation. So drill deep enough to get into, to test any deeper lithocaps, plus test the feeder zone and find the feeder zone, because that's where you're going to have the highest grades. And now Loma Larga has 2.2 million ounces, sufficient for at about 4 or 5 grams gold, 4.9, 4 grams, 5 grams gold, sufficient for underground economic development of this deposit if they eventually can get their regulatory approvals from the government. Well, Yanacocha was discovered in the mid-80s, went into production went into production in 1993. Then Parina was discovered in 1996, quickly into production. Alta Chicama was a big deposit, discovered in 2000, went into production in 2005. That's the Lagunas Norte deposit that I've mentioned. However, southern Peru was known as a silver district, Orcapampa, Arcata, Cayoma, etc. So these large gold companies that had these large gold deposits thought, why should we explore in southern Peru? Because these are epithermal silver veins. Well, there was a company, Arantani, that decided to look at one of their projects of silver base metal veins and ask the question, what about the potential for this type of lithocap hosted mineralization? They found a small deposit in 1997, a large deposit in year 2000, put them into production very quickly, and that led to gold fields coming into this southern Peru, making a discovery along with Buenaventura in 2008. So that dogma was, well, there's only silver there. We don't need to go explore for gold in the silver district. It's now been proven wrong. And since 2002, there's been 400 tons of gold discovered and produced from southern Peru in epithermal high sulfidation deposits. This is the Tucari district, the Arantani district in southern Peru. And this was a discovery of new gold enargite style deposits in an area that previously had been mined for silver lead zinc veins. This is the Peruvian group that made the discovery. Wolfgang Morsche is a volcanologist who mapped the volcanic rocks in the area, and I was very glad to be visiting at this stage to see their successes. Here's the area of The prospect, we can see Titicaca is just to the northeast, and this alteration map, outlined in blue, the white areas, was determined by Alvaro Crosta based on Landsat TM. Well, the first deposits, the deposits mined in this area were Cacachara and Pavico, small silver, lead, zinc, intermediate sulfidation veins. But then Arantani geologists went back and discovered the Santa Rosa lithocap, very close to 3-4 kilometers from Pavico and Cacachara, as well as then finding subsequently the Tucari lithocap. And Santa Rosa, small amount of gold, 0.4 million ounces, Tucari, much more, 2 million ounces of gold. So here we are, only 3 to 4 kilometers from the Cacachara-Pavico intermediate sulfidation veins. Remember those veins that sit on the margins of the lithocap in Silito's porphyry gold system schematic? The lithocap is there with the intermediate sulfidation veins on the margin. Same here. So Arantani was able to discover the lithocap mineralization, even with still opaline silica capping the alteration, the hill here, Cerro Cotignani Hill, so very shallow level of erosion. And here we see the opal, and here is the feeder zone of residual quartz and some massive quartz mineralization. The feeder zone followed a permeable lithology of tufaceous rocks flaring off laterally, very similar to Nansatsu deposits, Iwato I showed earlier. And subsequently, they made the discovery of the Tucari deposit, all residual quartz. First, we'll look at a cross-section through this part of the body. We can see the Barossa andesite volcanic rocks. They're not a very good host for hydrothermal systems, but related to the younger intrusion of these porphyritic dacites, these dacite domes. And as you will see of the alteration, the dacite dome is what's related to mineralization. Here we see residual quartz after the dacite dome and mineralization greater than a quarter gram per ton gold and supergene oxidation within that altered dacite dome. So that was the discovery and the characteristics of that Tucari deposit. After that discovery, it was clear there was significant gold potential in southern Peru, and that reawakened the interest. Here we're see the Arantani crew drilling at the base of the lithocap at about 4,980 meters, drilling down into the top of a characteristic alteration of a porphyry style. So there's a porphyry system. So there's likely a porphyry system at depth. Whether or not it's mineralized, it'll take more drilling. Well, subsequent to that discovery, Arantani District, Goldfields, and Buenaventura joint ventured in the Chuquipaca District, and they assessed this dome, very similar to the dome at Tucari, except that they had relatively low grades. Locally, they would get a 0.5 gram gold. They had some drilling of 0.8 grams over 10, 20 meters, but just not very significant here. Although over the area of oxidation, supergene oxidation in the sediments, there was 1.1 gram per ton gold. Well, Goldfields decided not to pursue this after drilling 6 holes here, or maybe 10, but they turned this over to their joint venture partner, who were interested in the sediments. They drilled 5 holes looking for zinc in altered sediments, no zinc, no gold. The sixth hole, the last hole in the project, no zinc again, but they cut over 100 meters of 1/2 gram, 2 grams gold. Well, that led to the discovery of the Kanuiri deposit 3-4 kilometers away from the dacite dome center of the district. It's now called San Gabriel, but it's not a Gaussian, it's a pseudogaussian because it wasn't supergene oxidation of sulfides, but rather oxidation of anchorite, iron carbonates. Buenaventura made the discovery in 2008. Eventually, Goldfields backed in and drilled out and identified 230 tons of gold equivalent in this area, 3 to 4 kilometers west of the Chuquipaca Dome complex with residual quartz alunite. This deposit is related to a diatreme. We can see here the juvenile clast within this diatreme. The diatreme is not the host, it's the margins, brecciated margins in the sediments that host the mineralization of intermediate sulfidation style chalcopyrite sphalerite mineralization along with gold and. So again, carefully assess the whole district, not just something you're targeting, but the whole district for other alteration styles, other mineralization styles. Think laterally, figuratively, but also in this case, literally. So I'll have one more example, and then we can open it for questions up to 6 o'clock. The next, let's wait until the last presentation. Okay. This is transition to the porphyry from the lithocap. Again, not a lot of time to go into details. Back to Yanacocha, we have several ore bodies in through here. The largest, Yanacocha Norte, 25 million ounces. But in addition to the lithocaps that have gold mineralization, we also have Kupfertal. In German means Copper Valley. And we're going to go from the San Jose deposit, produced 4 million ounces of gold, walk down into Kupfertal. Because as we walk down, halfway down into the valley, we start to see residual quartz being replaced by porphyry and nodules. And if we get to the bottom of the valley, drill holes that cut muscovite at depth, at shallow levels, there was porphyry, alunite, kelnite, and some of the drill holes also cut through this nodular porphyry. Basically, that was at the base of the lithocap. How does that porphyry form? Well, some porphyry forms next to the residual quartz alunite, kelnite, diaspore. You can even get porphyry at higher temperatures in the roots, like at Quimsacocha, Loma Larga, but that's acid conditions. However, we can also get porphyry forming as muscovite cools. For example, here at El Salvador porphyry in Chile, we have muscovite andalusite zone with muscovite andalusite in thin section coexisting, but then porphyry overlying. Why? Simply because as we cool along the andalusite muscovite join, we cool into porphyry stability at constant KH ratio. No need to have acid conditions. So this porphyry, muscovite to porphyry, answering one of the earlier questions, is basically indicating cooling, cooling below the lithocap. And we see that here in Yanacocha, in the base of the valley. Sometimes the nodules coalesce to sort of wormy or gusano types of textures. We see it at Oyotogoy in Turkey, in lithocaps near porphyry, in central Chile, where the porphyry has been eroded out, weathered out, very near 10 kilometers away from a world-class porphyry. And here at Lagunas Norte, the Milagros porphyry prospect, the nodular porphyte, diaspore, pyrite, and here the porphyte is replacing quartz. Why? Because muscovite, as it cools, it needs silica to form porphyte. And so that is why we're getting the replacement, the nodular replacement of porphyte after quartz just over the muscovite zone. Well, this zone, there was stockwork in the bottom of Kufetal with overprinting porphyte, kaolinite, etc. The drill holes cut through porphyry stockwork and basically defined the Kufetal porphyry at depth. Now the Corimayo, the alunite of this lithocap, 10.76. San Jose, the alunite of this lithocap-hosted gold deposit, 10.73. The biotite of Kufetal porphyry, potassic porphyry biotite, is 10.73. They're all the same age. So our early explanation for the brine vapor separation, vein condensing, vapor condensing to form the lithocap style of alteration in alunite at the same ages. The biotite here is related to the deep porphyry brine. The alunite here is related to the vapor condensation. And overlying in this valley would have been muscovite, porphyte, not residual quartz, because as the fluids ascended shallow levels, they started flowing laterally along the lithocap horizon and cooling, forming more residual quartz on the margins. In contrast, directly over, it was still too hot, staying in muscovite porphyte. That's what formed here, and that's why it was eroded, as opposed to lithocaps extending over the top of this valley. Okay, so Yanacocha in this part of northern Peru formed at 8 to 12 million years ago, whereas to the east we have older 16 million year porphyries formed, 21 million year porphyries formed, now exposed due to erosion of this older area. At Parol, there is a lithocap 10 kilometers east of Yanacocha. There's a lithocap called Saracoqueñas with quartz alunite, but low grades of gold, 100 ppb gold or less. Well, the Newmont geologists first came here, they went back to Yanacocha. They weren't impressed with this lithocap. Subsequently, a group from Sedimine came through here and they stopped their mules in this area, and there was a practicante from university who had a lot of energy running around, and the practicante saw some outcrop, pulled the soils back, and found this sheeted quartz vein. He took a sample back to the senior geologist. What's this? That's porphyry copper veins. And that was a discovery outcrop by a practicante from the nearby university who made this discovery. 640 million tons, 0.3% copper, 0.7 grams gold. That was a discovery of Parol. And in fact, the Parol orthoclase, potassic orthoclase, has an age of 15.8 plus minus 0.18 million years, overlapping with this alunite. So it's quite possible that this alunite lithocap, coarse-grained lithocap, is the corresponding lithocap to this porphyry, again on the margin, forming on the shoulders of the porphyry deposit. So in closing, last few minutes, we have our intrusive center, porphyry, the lithocap developed, residual quartz may be host to epithermal high sulfidation deposits, or on the margins, epithermal intermediate sulfidation veins, overlain by steam-heated acid alteration. And these are the various deposits that we have looked at today. So there's nothing magic about it, no magic techniques or tools, just good geology, which requires good geologists, good training. All the people listening here. Don't try to squeeze your deposit into a model. Rather, make your observations, describe and interpret what you're seeing, and think laterally in the epithermal environment particularly. Helps to have experience, but think laterally, figuratively, as well as, of course, literally. At that point, Stalwin, I guess I have about, I think I see 6 minutes left. We can answer some questions before we close this lecture and go to the next.
Yeah, I think we can handle 2 questions. So it was from Inti Claro. How does the magmatic affinity alkalinity series affect the hydrothermal alteration and the ore grade?
Well, by magmatic affinity, you mean silicic to andesitic. Mafic rocks, you sometimes get diorites forming porphyries, but then quartz diorites through to other rocks, of course, alkalic as well. And, I'm not, of course, mafic rocks I don't know of any mafic rock that is forming a porphyry, really end member mafic. But there's a wide range of rocks. In terms of magmatic affinity or magmatic fertility, I'm not a big believer in magmatic fertility. I think all intermediate to felsic magmatic magmas potentially can form a porphyry deposit. You need the right crystallization pathway, the right large enough volume and age of systems, as opposed to some being more fertile than others. I think it is up to the hydrothermal systems to decide whether or not the deposit is economic. Next.
Yeah. This will be the last one. Sorry for the time. I should have asked you for 3 hours. So Juan Rosa said, if the Chalcedony silica zone is known in a high sulfidation deposit, how deep can the advanced argillic alteration zone be?
Well, the paleogroundwater table, defined by opaline silicification, chalcedony, conchoidal fractures, that can be, that groundwater table, as we've seen from some examples, can be many hundreds of meters over the base of the lithocap, easily 500 meters, 800 meters. So if you have paleogroundwater table preserved, you're going to have a thick sequence of lithocap. To assess for potentially high sulfidation deposits or on the margins, intermediate sulfidation, the epithermal potential is still there until you've proven or disproven it, but you're going to be drilling very deep for a porphyry target. Okay.
Okay, thank you, Jeff. Before we finish the presentation, I will share my screen. So please don't leave.
Yeah.
Wait.
I see a lot of chats there. I'm sorry for not getting to everybody's questions, but if Stallman, if you want to send those chat questions to me, I'll answer them and send them back to you.
Okay, are
Yes,
you
I am.
seeing my screen now? Are you seeing the
Yes, I
document?
do. Thank you very much. It looks
Okay,
great.
yeah. So, so, Jeff, on behalf of the SEG student chapters in the Andes, we sincerely thank you for sharing your expertise with us today. We truly appreciate your time in contributing to our academic formation. And as a token of our gratitude, we would like to present this certificate of appreciation, which reflects our deep respect for your contribution to our chapters. And once again, thank you for being with us today, and we look forward to staying in touch and hope to welcome you in the future.
Thank you, Stallman. Thank you, David, the chapters of Quito, Ecuador, and also thank you to everybody who's been listening in from north to south. I just took a screenshot of the certificate, so thanks a lot, guys, and good luck with your next lecture, which is starting in about 1 minute, I think. And thanks for all the notes of appreciation coming in. Much appreciated. Go ahead. Okay. Bye. Let's see.